Okay, good morning, everybody. I think it's a good time to start today's session, which will be on onboard interconnects. The session will be opened by someone coming from very far away from Keio University in Japan. It's Professor Ishigure, and he will be talking about design and fabrication of multimode polymer waveguides for PCBs.
Thank you very much for your kind introduction. Good morning, everybody. My name is Ishigure from Keio University, Japan, very far from here. And last week, I was attending a conference, ECTC conference held at Florida. So now my time is in between the US, Japan, and Europe. I'm not sure where I am. Anyway. So today is a very beautiful day, so thank you very much for coming from such an early morning. And I'm very happy to give a talk here. So I'd like to thank Nikos Peras and the other related committee people. My talk today is design and fabrication of multimode polymer waveguide for PCBs. And I'd like to show you a little bit weird technique to make a polymer waveguide. Because several previous speakers are mentioning about this chart, so I'm going to skip why the optical interconnects are required. And this is the current status of optical interconnect, where at the edge of the card, the signal, electrical signal is converted to optical, and in between cards or rack, already multimode fiber bundles are deployed widely for high-end servers and supercomputers. And in the near future, here is the boundary between electrical and optical. But in the near future, it is already started to be deployed, that the edge is coming closer to the LSI. And then next step is how to route the signals in using the fiber bundles. It may be causing some kind of jam like this. Therefore, we are focusing on optical printed circuit board on which multimode polymer waveguides are incorporated. And then from the edge, as already deployed, multimode fibers connecting these PCBs. That is our focus in my talk. And here are typical polymer materials for making waveguides. Widely used accurate one from Korean company, or true mode would be very famous in this European community, I believe. And epoxide, siloxane material, and polynorbonane is a very unique material. And polyimide, polysilicon, and fluorinated polymer. There are so many players. And in general, the required specifications of polymer materials is, as you can imagine, the low optical loss at hopefully at 850 nanometer or 1060 or longer, like 1310 or 1550 nanometer. In addition to these optical characteristics, for optical PCB applications, high thermal stability at 260 degrees C is preferable in order to apply to solder flow process. While long-term stability at the temperature of other electronic components are also required, like 85 degrees C, 85% RH. And application to photolithography or UV cable is another specifications for polymer material. And then this is a typical loss spectrum where at 850 nanometer, currently 0.0 less than 0.05 dB per centimeter is required for at least 50 centimeter long distance link. While you can see several peaks in the attenuation spectrum. That is coming from the absorption due to carbon hydrogen that is inherent in organic polymers. Therefore, as I mentioned, fluorinated polymer is a candidate in order to decrease this polymer inherent absorption loss. Because if we substitute a carbon-hydrogen bonding for carbon fluorine, because fluorine is a heavier atom than hydrogen, we can decrease the absorption. We can actually shift these peaks to longer wavelengths. And however, for multimode applications, normally VCSELs emitting at 850 nanometer is widely used. Therefore, we do not have to care about the attenuation at longer wavelengths here, and we are mainly focusing on this 850 nanometer wavelength. And because of the specifications I mentioned, in general, multimode polymer waveguides having these structures. Normally, the core has a square shape like this way, and the core size is 50 micron times 50 micron, or less, like a 35 micron. And the refractive index in the core is flat. We are calling this structure as a step index type. And pitch is now reduced to around 62.5 micron, but it used to be 250 micron. And the light signal injected into the core is reflected at the core cladding boundary due to the difference of the refractive index. This is well-known schemes you can see in the textbook of fiber optics. However, in the case of this step index type waveguide, we are concerning about these two issues. One is what may be the large propagation loss, because if the core cladding boundary is not smooth, the light is not completely reflected, but scattered a little bit. And then by repeating this reflection at rough core cladding boundary, it may be causing excess scattering loss. And then for a higher density core alignment, the pitch is no more to 50 micron, as I mentioned, 62.5. Then the closer cores can receive the scattered light from the main core. It may cause a crosstalk. So, however, so far, this kind of multimode polymer waveguides are well developed, and these are demonstrations in OFC or ECOC, and we could see some demonstrations on ECOC 2013. And mainly, the multimode polymer waveguide links are composed like this way: on-board polymer waveguides, on-board again, and these two cards are connected with graded index multimode silica fibers. Therefore, our proposal is introducing the same structures as the multimode glass fibers into a polymer. That means graded index circular cores in a polymer. If we can realize these structures in polymer, we can expect these three advantages: low propagation loss, because in a graded index core, the light is no more reflected at the core cladding boundary, while refracted due to the refractive index distribution. And the light trajectory is like this sinusoidal one. And you can see the light is not reaching to the core cladding boundary. Therefore, we do not have to care about the core cladding boundary roughness. Then, even if the cores are coming closer, we don't have to care about high crosstalk. And as you know, the fibers connecting the two waveguides having the same structures, circular core, graded index. We do not have to care about the modal field mismatching between the polymer waveguide and the fibers. Therefore, high coupling efficiency with a fiber is another advantage. So let's move on how the structure is increasing the coupling efficiency between the fibers and the waveguide. This is a theoretical simulation. We suppose the two polymer waveguides having these three wide variety of structures, a circular core graded index, or a square core step index, or another GI. Fiber has also GI circular core. But for polymer waveguide, we are supposing two different structures, square, SI, GI circular. And here is the result. This dotted line is the connection point with polymer multimode polymer waveguide and the multimode fiber. And these are optical intensity field. In 50 micron square core step index waveguide, whole modes are extended to whole core area, while in graded index core multimode fiber, due to the concentration, the optical concentration into the core center, the field is completely different. On the other hand, when we use 50 micron GI circular core polymer waveguide, the modal field mismatching is not observed from this chart. And even if we use 50 micron square GI core, we can expect the similar effect to circular GI core as well. And here is the coupling loss between multimode waveguide to fiber. This axis is the core size, and this is the coupling loss. In the case of the SI square core, when the core size is 50 micron, because the square core and the circular core does not well fit. Therefore, their high losses are observed like this way. Therefore, in the case of step index square core, the core size should be smaller than the size of multimode fiber. And currently, 30 to 35 micron would be the optimum. On the other hand, in the case of graded index core, even if the core size is different from the multimode fiber core size, very low coupling loss is expected. On the other hand, because we are supposing the multiple connections between the waveguide, fiber, and the waveguide, there are three connection points from the beginning of waveguide, connection point 1, light source to waveguide is the connection point 1, and the 2 is here, and 3 is again from the fiber to waveguide. In this case, GI circular core is not the optimum because of the modal field mismatching, while square core GI shows a wide tolerance in the core size in this case, while step index square core shows the lowest coupling loss when the core size is 30 to 35 micron. Therefore, from this result, we start our research to fabricate graded index core multimode waveguide. Okay? So the next topic is how we can realize that structure in polymer. We developed this very unique method named the mosquito method. In the mosquito method, we are using micro dispenser. This is a desktop robot, and in this part, we can set the syringe with a thin needle. In the mosquito method, at first, we are coating liquid state monomer for siloxane-based resin, UV curable, very high heat resistance polymer. But this is liquid on a substrate. Then a syringe that has a thin needle is scanning this way to right core, parallel core. And then after making this structure, just UV exposure for killing both core and cladding. Why the name is mosquito? Because the tip of the needle is injected into the cladding monomer like this way, not on the cladding monomer, inside of the cladding liquid monomer. You can imagine that why the toothpaste is maintaining its round shape on your toothpaste, because the toothpaste has high viscosity. We are applying that mechanism on this. High viscosity core monomer is injected into liquid monomer. So we are using this desktop robot, and this is a syringe, and you can see the movie like this way here, core dispensing. This is actual speed for one core, the neighbor cores, and then we can use just UV LED for cooling. So we do no more need any UV exposure machines like high spec. And then the waveguide size is not limited by UV exposure machine, but just the stage size of this robot. So if we can obtain a large size stage for the robot, we can make 1 meter length or higher, longer length of waveguide. And why the refractive index profile is obtained? Because you can also imagine that the toothpaste is squeezed into water. Then water is coming into the toothpaste, diffusion. The same thing is happening in this cladding material. The liquid cladding monomer can diffuse into the core to make the concentration distribution. Because the core monomer has a higher refractive index, the concentration distribution is leading to the parabolic refractive index distribution. Therefore, for making the graded index core polymer waveguide, we are paying attention to these 4 parameters. One is dispensing pressure. The second one is scan velocity. Of course, the needle inner diameter is very important to obtain a thin core size. And viscosity is another very important issue. So we were wondering how we can obtain such a thin size core, like a 50 micron from a needle, because the core monomer has high viscosity. However, it is very easy. You can see these parameters, scan velocity and the core, this is the core diameter. And in this case, we used 2 different dispensing pressures. From this chart, you can see with decreasing the dispensing pressure, we can obtain a thinner core diameter. And you can see circular cores are obtained like this way. And with increasing the scanning velocity, it is very easy to imagine that we can also decrease the core diameter. And it is surprising that from 190 micron inner diameter of the needle, we could obtain almost 60 micron core diameter by just adjusting the dispensing conditions. And when we use a smaller inner diameter needle, this is in the case of 150 micron, we could reach less than 50 micron diameter core. And circularity is very good. And by changing the dispensing conditions, we can obtain not only smaller core, but also a larger core. And here is obtained waveguide. This is 50 16 centimeter long waveguide. And here is a refractive index profile actually measured from this interference fringe patterns. And this is a 3D expressions. You can see a good parabolic refractive index is formed in the cores. And then we are evaluating optical characteristics and comparing to existing step index square core. So far, we could not have the same the step index and graded index waveguide composed from the same material. Therefore, we haven't evaluated a fair comparison between the SI core and the GI core. However, this material, siloxane-based material available from ADEKA Corporation, Japan, not only graded index core, but also step index square core waveguide is fabricated successfully. This is fabricated by ADEKA Corporation, not by us. So now the core size is same, and the pitch is also same, and the length is the same. Then first, this is the optical loss spectrum. At 850 nanometer, 0.033 dB per centimeter is available. And as I mentioned, because the graded index core is not using the total internal reflection scheme, we could decrease the excess scattering loss at the core cladding boundary. And then we compared the insertion loss between two fibers. That is not only the propagation loss inside the polymer waveguide, but also the connection loss between fiber and waveguide are included. In the case of graded index core waveguide we made, when the single mode fiber is used for launching the cord, the insertion loss is slightly smaller than the case of step index. And in other launching conditions, always the insertion loss is lower than step index counterpart. That means not, in this case, the propagation loss of these two waveguides is almost the same. So this difference of insertion loss is coming from this coupling loss. As I mentioned, in the case of graded index core, due to the mode field matching, the coupling loss between the waveguide and fiber is lower than the case of the SI waveguide. And now we are introducing how we can form the fine pitch parallel cores. As you saw, the parallel cores is obtained by repetitive scan of the one needle. That may be not efficient, but it's very important to design or freedom on the waveguiding structure. Okay, in this case, for 250 micron pitch, that is good, large enough, because the outer diameter of the needle is now 350 micron. Therefore, the formed core previously dispensed is a little bit far from the edge of the needle. Therefore, even if we apply the multiple scans, the core alignment is not affected by this needle. On the other hand, in the case of half pitch, 125, no more wide tolerance is obtained, but the edge, the formed core is now within the outer diameter of the needle. Therefore, in the process of the multiple scan, the core alignment may devastate. So we evaluated the needle tip height and the core position in detail. In this experiment, we deliberately varied the needle tip height from the substrate like this way. And the initial point, the height was preset to 50 micron higher than the substrate. And with a 30 micron step, the needle tip height is widely varied. And here is the result. In the channel 1, no circular core is obtained, while good circularity is obtained in this area. And here is the numerical result. You know, at channel 1, the circularity is not as high as 1, while it is reaching to almost completely circular shape like this way. The interesting thing is that this white square plot is showing the preset needle tip height, while this red square is actually measured core height. From this result, we can see that about 30 micron difference between the preset core tip height and core position is observed. That means after dispensing the core is immediately pushed down in the cladding due to the dispensing pressure. That is very good, because even if we scan multiply, the edge of the needle is not affecting the core alignment. Then we could obtain a half-pitch micron size parallel cores like this way, and a very good uniformity, and even 62.5 micron pitch is successfully obtained. The average pitch is not 62.5 micron. This is because the preset value for desktop parameter is not 62.5, but just 62, because the minimum pitch set value is just 1 micron. We cannot preset for less than 1 micron. That is why we preset the pitch value to 62 micron. So we evaluated how the pitch is uniformly controlled by connecting with fiber ribbon with a pitch of 125 micron that is available for full-color electronic. The measured pitch was now 125.0 plus minus 0.9 micron. But after transmitting through this waveguide, we could see a 12-channel near-field pattern like this way. That means good connectivity with multimode fiber ribbon is available. So we can see GI circular core waveguides with precisely controlled narrow pitches are fabricated successfully for the first time to the best of our knowledge. And then, in such a narrow pitch waveguide, how the crosstalk is increased. We evaluated the interchannel crosstalk in this 250 micron pitch GI core and SI core and a half pitch one. Here is the result. This is the optical power from launched core and adjacent cores. In the case of 250 micron pitch, the adjacent core is here, and the second one, third one. And 125 is in the middle. And you can see the higher output power from the SI core waveguide is observed, not only from the core, but also from the cladding. It is very interesting that at the core, the output power is decreased like this way, suddenly dropped. This is because of the connection efficiency between the waveguide and the fiber. And in the case of graded index core, always the output power is lower than in the case of the SI type waveguide. And evaluated crosstalk value is here. In the same pitch size, the crosstalk is 10 dB lower than this one, and in the case of the half pitch, almost similar crosstalk is observed. And this less than 30 dB crosstalk is low enough. But from this result, we can say higher density core alignment is available from GI core waveguides. And this is a high-speed power transmission experiment for 12-channel cores. Again, highly pitch control waveguide is inserted into two 125 micron pitch multimode fiber ribbon. And all through 12 channel, we transmitted 11.3 gigabit per second signal. And good eye opening is observed from all the channel like this way. That means good connectivity in these two fiber ribbons. That means two connections are available. So not only at this facet, but also at the other end, the pitch is well controlled. And here is the bus-stop curve. And even in the case of 125 micron pitch, the interchannel optical crosstalk is not affecting to this transmission characteristics. So this high pitch control technique is now published in Optics Express April issue in this way, and we are very happy that this article is selected for Spotlight on Optics on May 15th. So this Optics Express is, as you know, freely downloaded even from your home. So please visit this site. So by this mosquito method, not only straight waveguide, but also this kind of curved waveguide can be easily obtained. So in this case, the bending radius is 15 micron, and we can reduce the bending radius to about 1 millimeter. And in this case, the circular core is well maintained. And this is the result of one bent case of the bending loss. Actually not the bending loss, but just insertion loss for this 7 centimeter long waveguide with one perpendicular curve. In the case of a large bending radius, the insertion loss for 7 centimeter is around 2 dB. And on average, 3 dB and on average. And with decreasing the bending radius to 3 millimeter, the insertion loss increases. That is mainly due to the bending loss. In this case, the numerical aperture of this waveguide is as low as 0.2. Therefore, we need to increase the numerical aperture for decreasing the bending loss. So now, in the case of 0.28 of NA, even under a 3 millimeter bending radius, the insertion loss is as low as 2 dB. And that means no additional bending loss is observed in this case. And 0.36 NA case, you can see even under 1 millimeter bending, no more additional bending loss is observed. And now we are trying to make this kind of S-type waveguide. And now my students are evaluating the bending loss. So in the next opportunity, we are going to show how the bending loss is observed. And my title is multimode waveguide, but we can decrease the core size even to less than 10 micron. That means the single mode waveguide is now available by the mosquito method. Here is the cores. And in order to decrease the core diameter, high scanning velocity is very effective. In this case, we need to dispense the core monomer with a high pressure. While when we decrease the scanning velocity, we need to decrease all the dispensing pressure also. But by adjusting these parameters, we can obtain less than 10 micron size core is successfully obtained. And we evaluated the insertion loss of these waveguides. And now the core diameter of 12 micron showed the best insertion loss like this way when these waveguides are inserted in 2 single mode fibers. So we still need to optimize the dispensing conditions for obtaining good single mode waveguide. And this is the presented data at ECTC last week. And by applying this mosquito method, 3-dimensional wiring is also possible. So we tried to fabricate this kind of found-in and found-out waveguide. Here, the core alignment here is obliquely, like this way, 3 core. At the other end, these 3 horizontally found out, not only horizontally, but also vertically, this core height is adjusted to obtain a horizontal alignment. Then a 3D needle scan is required, but we could obtain this kind of structure. And good light transmittance is observed. And then we increased the core number to 5, and then we succeeded. And finally, we tried to fabricate 7 cores for fitting to the structure of multi-core fibers like this way. At the one end, the hexagonal stack of the core is formed, while at other end, these 7 cores are widely open to 250 micron. And so at the final part of my talk, we would like to mention about PCB circuit with crossed waveguide structures. That topic is already mentioned by previous speaker yesterday. As you know, in one plane, not only straight and curved structure, but sometimes waveguide crossing is needed. So previously, step index core crossed cores successfully fabricated, and we just picked up the 3 examples in year 2000, 2004, and 2009. But in this case, as I said, in the case of step index core, the light is reflected at the core cladding boundary. So at the intersection, there's no cladding here. So some light may be leaked out like this way. Therefore, in this case, 0.1 dB per crossing loss is observed, and it is improved to 0.02 and 0.01. But in the case of graded index core, we expect that this kind of excess loss due to crossing may be decreased because, as I mentioned, for light propagation in graded index core, we don't need cladding. So we simulated the crossing loss in graded index and step index cores with using ray tracing simulation. Here, this is the condition for the waveguide and the index profile for core in horizontal direction and vertical direction. And here is the calculated result. This is just a simulated result. With increasing the crossing number, the loss at per cross in SI waveguide decreasing because at the initial stage, higher order mode with frequently colliding to the cladding is leaked out. And then there is a small possibility to be leaked out at the intersections in the case of SI waveguide. While in the case of graded index, very low crossing loss can be expected theoretically. And this is accumulated loss. And you can see the gradual accumulated loss increment is observed in the SI, while GI has very flat low loss is expected. So very low loss in GI core despite the SI. This means that At the cross-section, it is very difficult to suppose the graded index structure in both directions, from the point of fabrication process. Therefore, for the simulation, we suppose that at intersection, no more graded index structure is formed, but just flat uniform refractive index is dominating this intersection. That is our that we suppose. However, despite the SI core structure at the intersection, the very low loss in graded index core is calculated. So, how we can fabricate this GI crossed waveguide? Is it possible by the mosquito? No, unfortunately. We can have this kind of overhead crossing is possible, but unfortunately, the crossing at the same plane is not possible by this mosquito method. Then I'm going to introduce the photo addressing method that is developed by Sumitomo Bakelite. Okay, here is the schema of the photo addressing method. Richard Pittman already mentioned yesterday, just using a photo mask. And through the photomask, the UV exposure to the core monomer film. Then the area that UV is eliminated, the curing reaction occurs. While the shaded area, no chemical reaction occurs. Then the monomers in this shaded area gradually diffuse into this illuminated area due to the volume contraction. Then concentration distribution in horizontal direction is formed. That is the mechanism to form the graded index structure in this square core. And this is a very high secret, so I do not know how to adjust this condition. But not only horizontal direction, but also vertical direction, they could reach the concentration distribution to obtain completely graded index structure. So we name this structure GI profile, while this one we say SI-GI, right? Okay, so here is the mechanism. After UV cured, this illuminated area, the cross-linked structure is formed and the volume contraction is observed. Then some monomers are diffusing into this illuminated area. Then the concentration of this monomer is higher to decrease this, the refractive index in this area. And then graded index structure is formed. By applying this photo addressing method, this kind of perpendicularly crossed waveguiding structure is successfully fabricated. And not only perpendicular, but also other crossing angle is available. And again, a graded index profile is formed in this straight field, not at the intersection. Here, again, this is the number of crossing, and these plots are measured values. Here, unfortunately, the photo addressing method cannot make the step in the SI structure, so that this measured value is coming from this literature, 0.12 dB per crossing. So simulated results is slightly lower than this measured value, while good agreement is observed in between these graded index square core crossing waveguide, cross waveguides. So when the loss per crossing is 0.1 or 2, the slope is like this way, and 0.01 dB is showing this slope. So that even from the lowest value of the SI crossed waveguide case, very, very low crossing loss is observed in the case of graded index core. That is because the light in the core is not reaching to the cladding, well confined in the core. That is why, even if the cross structure is formed, the light is not caring about that structure, just go straight in the core. So the loss of GI core is one order lower than the lowest results of SI, 0.0019 dB per crossing. And again, in a different crossing angle, always very low loss is maintained in the case of graded index, and good agreement is observed between the calculated result and a simulated result. So I'd like to conclude my talk. We introduced the advantage of graded index core waveguide as follows. Low propagation loss because of the smaller effect of the core cladding boundary roughness. Low interchannel crosstalk even under smaller pitch due to the optical confinement in the core. Low connection loss with an MMF, multimode fiber, and low loss in waveguide crossing. So GI core polymer waveguides will pave the way for realizing high speed and high density onboard optical interconnects. Thank you very much for your kind attention.
Thank you very much for this impressive work.
Thank you.
And a comprehensive presentation. So, please, your questions. Yes, very interesting presentation.
Thank you.
I really enjoyed. Very tricky question. You don't need any temperature to promote the diffusion process?
Yes, for both cases, for mosquito method and the photo addressing method, we are now using just room temperature. So for larger core, we need to wait for sufficient diffusion. But for 50 micron or 100 micron, the required diffusion distance is not so long, so that normal temperature is good enough.
It's good enough, but alternatively, you could carry out also some experiments with a bit elevated temperature to see the effect. Have you done such experiments?
Yes. In the case of mosquito method, the viscosity is temperature dependent. So when we increase the temperature, the viscosity is getting lower, then sufficient diffusion is available. My pleasure.
How about the temperature dependence after the curing? So if the waveguide is after being fabricated, heated up to some value, so how much temperature can it withstand?
Yeah, after UV cure, the polymer has a three-dimensional cross-linking, so that normally the thermal stability itself is very high for our resins. But yes, the temperature dependence of refractive index is not clear yet. So the refractive index profile at high temperature may be different from that in the room temperature. So we need to evaluate it.
Any more questions?
Regarding the shape of the refractive index profile, I guess unlike fibers, this has a much wider tail maybe because of the diffusion. How did you measure the core diameter? What did you use as a metric to define the core?
Yeah. Actually, the core diameter definition is very difficult. So now, the core diameter we showed in this slide. Okay. All right. The core diameter we showed, for example, this is just measured from this photos taken by the microscope. And as you can imagine, the contrast is very important between the core and the cladding. So some deviation of the core diameter may be included in this observed core diameter.
Some pictures for your mosquito metal, some waveguide beneath your core, waveguide core, some drifting or well-shaped pictures.
Ellipsoidal shape?
No, some pictures underneath the core waveguide, there's a whole.
Yeah. Right, you're right. You mean this? Some people are imagining that the needle is inserted from this way, but no, that this is substrate and the needle is inserted from the upper surface. So we are not sure yet, but this may be coming from some intensity difference of UV, because UV light is coming from this direction, and then due to this core, it may be focused, because like a lens effect. Higher refractive index with circular shape, then the UV is now passing through the cladding, then refracted due to the lens effect, and may focus somewhere around. So this UV intensity difference may cause this shape, but the refractive index of this area is the same as the other area, so that this is not causing any bad effect on the transmission characteristics.
Can I ask if you have done any studies on the misalignment tolerance for this type of 3D index?
Yeah. Okay, as I mentioned, in the case of graded index core, the launch condition is a very important parameter for obtaining the small size near field output pattern here. So when we launch the waveguide using single mode fiber, that means a very small spot size launching beam is available. And that small size is maintained through this waveguide transmission. Then, here, this is, you can see here, 40 micron SI has a misalignment tolerance of 15 for 0.5 dB misalignment, while in the case of GI, the misalignment tolerance is wider than SI because of the difference of near field pattern. In the case of the SI core, the near field pattern is well spread out to the whole core. Sorry, this is written in Japanese. Maybe you I had the same impression when I arrived at the Greece airport. Wow, I cannot read any characters. Oh, some textbook of physics or mathematics. So you may feel the same feeling. Here, this is the step index core near field pattern. This is independent on the launching condition in general. So even if we use a single mode fiber with a small launching beam pattern, the whole core shows a bright output near field pattern. While in the case of graded index core, the light is tightly concentrated at the core center. That is the reason why we can obtain a good misalignment tolerance. And this is particularly for mirror. At the end of the 45-degree mirror, if the light is completely broadened to a whole core area, that spread out after the mirror. And then if the small photodetector is waiting, some light is not coming into the photodetector. While in the case of graded index, the light is well confined. So even if slightly diffracted from the mirror, it can go into the small photodetector. That is what this slide is showing.
I think your eye diagrams have been, they look very good. So have you tried to increase the bit rate of your testing?
For one channel, we already tried a 25 gig, and that is the maximum at this moment for VCSELs our colleague has. But first, we need to increase the waveguide length, like the last night poster from Cambridge group for 1 meter or longer. Then we should compare the dispersion and how high bit rate can be transmitted through such a long waveguide. So the next issue is how to increase the waveguide length.
Have you also tried these transmission experiments with your bands and your very big waveguides?
It's the next issue. Yeah, we hope so. Thank you.
Any other questions? I'll change now. Then Professor is going to go back to Japan. It's a little bit difficult to have.
Yeah. Yeah, I'm going to come back soon to Europe.
No more questions? Okay, let's thank the speaker again.
Thank you very much. I'm sorry that I shut down.
Okay. Ah, okay, yeah, there it is in front of my eyes.
Do you know the password?
Sorry? Oh, I don't know. Is that 1, 2, 3, 4? Okay. Okay, so our next speaker is Lars Brusberg, and I think it's a joint talk with Manessis from Fraunhofer IZM. They will be talking about single-mode glass-based PCBs.
Thank you. Good morning. So first I would like to introduce Fraunhofer IZM shortly. So Fraunhofer IZM is the Institute of Reliability and Microintegration, and it's located in Berlin, very close to the center part. And in the institute, they're working about 300 people in different areas. So the institute covers what's okay, thanks. So the institute works in areas and is focused on industrial-oriented applied research. So we're covering the whole area of electronic packaging, from design, fabrication on wafer and panel sizes, So using different materials, silicon, polymers, glass, and also textiles, and looking also on the reliability issues as well as environmental issues. So today we have a joint talk here about single-mode class-based PCBs. My colleague Dion will talk in the second talk later on. He's in the embedding and substrate group, and I belong to the optical interconnection group. And my research focus is glass-based packaging, photonic packaging. So here's the outline of our talk. So I will start with a short motivation for using glass as an alternative material for manufacturing of electrical optical circuit boards. And then I will introduce the fabrication process and give you a few characterization results for single-mode class waveguides. And then the second part, Dion will talk about the PCB embedding technologies and photonics in PCBs. Then he's talking about embedding of class single-mode waveguides in PCBs. So this is mostly work that we do in the Foxtrot project. And finally, he will conclude our talk. So I think most of you are very well motivated, but I also have a few slides, and I will go shortly over this. We have different areas where we have electrical and optical interconnects, and optical interconnects are very important. So we learned this if you have very high data rates or long distances for interconnection. And as we see here, if you have very long interconnection lengths in the telecommunication network, so single-mode fibers will be used for the core network. We have also optical interconnects for rack-to-rack interconnects based on active optical cables. There will be multimode fibers used for distance up to 200 meters, and at the moment also single-mode fibers will be used for distances up to 2 kilometers. Then we have really strong activities going on to manufacture polymer-based electro-optical circuit boards for board-to-board communication as well as chip-to-chip. But this is still on development stage. And of course, silicon photonics is a strong research activity to integrate optics into the silicon chip. At Fraunhofer IZM, we believe on our glass-based waveguide technology. So we work on the integration of single-mode and multimode waveguides into glass panels, and this can be used on all different interconnection levels. So everybody likes the slides of IBM, and I like it too. And here I picked a slide of Bert, and it was already shown that we have so far optical interconnects at the edge of the board, active optical cables, and it will be moving closer into the closer to the processors. So on the package, fiber-based, and also, and this is in development now, optical PCBs. And we have here we have here optical engines close to the processor located on the same package. And the final stage here is that we have the optics integrated into the processors. And then we need the silicon photonic technology, that we really have transceivers inside the silicon. And we also need, because silicon photonics works single-mode based in the telecommunication wavelengths, then we need also optical interconnects in the PCB that are single-mode and working in the telecommunication wavelength range. Yesterday, Tolga introduced us to the International Technology Roadmap of Semiconductor, and this forecasts an off-chip data rate in 2022 of 230 terabits per second. And this is an enormous value, because it's not realistic to do this with electronic assembling. And this means if this is coming to reality, So we need a lot of optical off-chip interconnects. So my talk is focused on how we can integrate single-mode waveguides into the PCB. So for this we need, of course, transceivers. So an optical path has an electrical interface, then we have the transmitter, converts electrical to optical, and then we have the optical interconnect, and then it's back converted from the optical to electrical. And so far, you can do this with parallel optical interconnects using high-speed VCSEL modulation, and you have all the components on top of an interposer. Then it's called active interposer. And you can also do this with silicon photonic devices, and you can increase bandwidth per channel by using wavelength division multiplexing. And this is another motivation to have single-mode waveguides in the telecommunication wavelength range on board level. So this is how our concept looks like. So we think we manufacture glass panels, and then we will embed these glass panels into the PCB. So we integrate waveguides in the panels. We have to integrate optical mirrors and micro-optics, so that we have an out-of-plane coupling. And we also work on glass-based transceivers, so that we have glass as a substrate material for interposers. And the question is, why is glass so suitable for electrical as well as optical packaging? And the benefit of glass is that the coefficient of thermal expansion is very close to silicon or 3.5 components, and this gives a higher reliability of electrical interconnects, so especially for the bumps. Then we can integrate through wires into the glass, and glass is an electrical isolator, so we don't need any passivation compared to silicon. So we swirl hools and then fill it with electric material. Glass has a high thermal load and has high dimensional stability. That means, especially for the embedding process, where we use temperatures up to 200 degrees Celsius, there's no issue that the glass will be deformed. Then glass is a transparent material, so it's well suited for integration of optics, waveguides, lenses, and so on. And it's very cost-effective materials. So display glass will be manufactured in high volume. So this manufacturing processes of glass, this panels having size of 3 by 3 meters so far. So this is state of the art in the display manufacturing. So we had already shown that our concept works very well. So we, for the electro-optical circuit board, for instance, we presented last week at the ECTC in Florida an electro-optical circuit board. This is a multimode optical circuit board, and this was also done in a collaboration project with Seagate and ILFA. So Richard mentioned this board a couple of times yesterday. And we had also shown that we can realize electro-optical transceivers using glass as an interposer material, and this work is was done a few years ago. So now I would talk about the single-mode integration in the PCB, and as already mentioned, we work in the Foxtrot project, and in this we have designed a demonstrator. So we will look on all aspects of onboard single-mode integration. So we have designed an optical backplane with an integrated glass layer. We designed line cards so that we can plug to this into this backplane by using board-to-board connectors, so that we have an optical interconnection between the integrated single-mode waveguides in the line cards to the waveguides into the board. We're working on a chip-to-board coupling concept. This is a mirror-based approach. So we have coupling elements with mirrors and micro lenses. So we will assemble electro-optical transceivers here, and there will be coupling into the waveguide plane. And we're also working on fiber-to-board interface so that we can optically interconnect the board to the outer world, to the fiber world. And here you see a closer look to the design. So this is the optical backplane. So we have a glass panel in the inner part, and on the edge of this glass panel we will mount this board-to-board connectors. Then inside we have the optical routing, and in the middle we will also have an optical chip. This will be a router chip, and on the side edge here we will have a 96 channel fiber interface. So the process flow is that we have to use glass panels coming from companies like Schott or Corning, and then we integrate our waveguides inside these panels. And so we have a waveguide process for this, and after we have finalized the process, finally we have processed the glass waveguide panels, then we have embed this into the PCB, and afterwards we will assemble our chips to this PCB, and finally we will mount all the optics. So this means the coupling elements, the fibers, and the board-to-board connectors. And now I will talk about this glass waveguide panel fabrication, and later on my colleague is talking about the PCB process. So that there are lots of glasses available from different companies like Schott and Corning, and we have to select the right glass that is suitable for our process. So one very important thing is that we have glasses that are available in panel or wafer format, so that we can really process it with our standard equipment. And the next point is that we have to select a glass that contains alkali ion, because we use an ion exchange technique, and this means we use glass that has inside the glass matrix sodium ions, and these sodium ions have very weak bonds, so they are exchangeable with other alkali or other monovalent ions, and then we can increase the refractive index of these glasses. So we use the ion exchange technology, and this is not a new technology. Actually, it's quite old. So it was used centuries ago for coloring window glass, for instance. Or it will be used from companies like Color Chip in Israel or from Leoni in Germany to manufacture splitters, so fiber splitters. But they are using a field-assisted ion exchange on very small substrate sizes. There are also companies that use the technology to manufacture lens arrays, and other companies use the technology to manufacture wide lenses for beam collimation issues. And Corning itself is using the technology to strengthen the glass. So I think most of you have such a glass in your pocket. So this is used to strengthen the cover glass of smartphones, and the brand name for this is the Gorilla Glass. I think it's well known. So you can really have a very strong surface that is crack, and it's very crack resistant. And we at Fraunhofer use this technique for manufacturing glass waveguide panels. So the process is that we use silver diode salt melts, where we put the glass in, and then we have an ion exchange. So this is the glass matrix, here is the salt melt, and then we have an ion exchange between the silver ions in the salt melt with the sodium ions in the glass, and there we can locally increase the refractive index of such a glass. And in this slide you see different glasses that we process with the same process parameters, and you can see the glasses are really different, very dependent on the glass composition. So the bulk refractive index is different, and also the diffusion characteristic. Some of these glasses have a very high diffusion coefficient. So this means in a very short time you can let move the silver quite far inside the glass. So this is, for instance, a Gorilla glass, because it's made for this kind of process. And you can also have glasses like the Gorilla. You can achieve a very high refractive increase. And there are other glasses, they're showing almost no increase, like Pyrex, because sodium content is quite low. So the process looks like this. So we start with the glass, buying them from Schott or Corning. Then we spatter aluminium on both sides of the glass. Then we structure this aluminium using lithography and etching steps. So we have a mask opening here. Then we put this glass in a salt melt containing silver ions, and immediately ion exchange between sodium and silver starts, and we have a refractive index increase only in this opening area here. And after a defined process time, we take out the glass and remove the aluminium and put it on a second salt melt. It's silver free, so it's containing only sodium ions. And then we see a back diffusion of silver ions that are placed on the surface, and there we can shape the refractive index to an elliptical shape. And finally we have our waveguides integrated below the surface. Now I would like to talk more in detail about our process and the equipment that we use. So we use an spatter equipment that is suitable for spatter panels and wafers. So far we have set up the process to a size of 210 by 297 square millimeters, and we spatter a 400 nanometer aluminium layer on both sides. Then we used dip coating or spin coating. So for the panels we use dip coating. If we use wafers, we use spin coating, and we deposit photoresist on both sides. And then for the exposure, we're using laser direct imaging or mask exposure, and we developing the resist, doing aluminium etching and mask removing. And here, this is a panel after the development, and this is a glass with the aluminium layer on the glass surface. And this is also the process step where you define the waveguide layout. So you can make a design on your computer, and then with the mask you transfer it to the glass panel. So we can have bends here, straights, crosses, splitters. But there are also some problems that can come up. So we also see defects, and this kind of defects influence the waveguide propagation. So we have to make sure that we don't have such kinds of defects. So this can be that we have mask openings that we don't want to have there, so like spots somewhere, or we have an interception like here. So this means the mask is not full opened, and we also have and disruption on the mask opening edge, like you can see it here. We can also control the pitch of the waveguides in this step and define the waveguide width, because this influences the diffusion process afterwards. Then we put these glass panels into a furnace. So such a furnace is not available on the market, not for this kind of process. So we have developed such a furnace at Fraunhofer, and here the benefit is, of course, because we use a thermal process, so we can really process lots of panels in parallel. So it's the panels will be vertically placed into the furnace, and yeah, it's very well for batch processing. And then we have a second lithography step, and in this step we can also save some features on the aluminium, because in this first aluminium etching step we can structure the aluminium for the waveguides, but also we can structure partner locus in alignment markers, and these alignment markers have very high accuracy related to the center of the waveguides. So for post-alignment processes, it's recommended to use such kind alignment markers for that. And then we place it again in such furnace with a different salt melt and forming the waveguide profile. And finally, we have to cut the panel to our final size. So there we have a laser cutting system in-house, and this works with in such a way that we have that we give an initial crack to the edge of the glass, and then we move this crack through the glass along a line, and this will be done by thermal stressing the glass. So we have a CO2 laser that heats up locally the glass, and just behind is is water cooling that cools it up the glass immediately. So this cracks really moves along a line, and we're getting a very nice optical end phase, and we can use this for optical coupling. So we don't need any post-polishing processes. So we can decide how we want to cut it. So if we have a panel, we can cut it to smaller pieces, or to just move the border around, so that we really have interface to such kind of panel. We can also cut wafers to smaller pieces for instance, PCB embedding tests. And it's similar with the wafer size process. So there we use spin coating and mask aligner, and the diffusion process is the self, and then we cut it. And for instance, for Foxtrot project, we cut glass lighters 20 by 90 millimeters, and then we find out what is the best embedding technology for such a single mode glass waveguides, and this will be presented later by Dion. And in Foxtrot we also manufactured already a single mode glass panel having 140 by 140 square millimeters with different waveguide structures, bands and crosses, and straight waveguides with different pitches. So if you look at have a closer look to the edge of this waveguide slide here. So we have the glass material. It is unchanged, but we have only changed the glass very close to the surface. We have increased the refractive index, and we have this waveguides here. In this case, we have a pitch of 125 microns. And because of the diffusion process, we get a gradient index profile, and this profile is about 5 microns below the glass surface, and has a refractive index different to the bulk glass of 0.003. And because the waveguides are very close to the glass surface, we had to find out how we can embed this kind of glass waveguides. So do we need another top cladding layer for this, or can we embed it without such a top cladding layer? And we study this in more detail, and this will show later in this presentation. So if we look on the waveguides profile, we have a mode profile. It's a little bit larger than a single mode fiber profile, so with a mode file diameter of 10 microns because of the elliptical waveguide shape. And so we have a mode field diameter of 12 by about 19 microns. So to see what's the losses for this kind of waveguides, we did a cut-back method, and we could measure the propagation loss, and we have really low propagation losses at 0.05 dB centimeter at telecommunication wavelength range. So and this means we can have really long wavelengths over a few centimeters with really low losses inside the PCB, and can interconnect the different chips on the PCB as well have chip-to-fiber interconnects there. And we have seen, in best case, we can also achieve very low coupling losses. This is one coupling interface for in-coupling. It's 0.26 dB. So this is the last slide of the first part of the presentation, and I will summarize our activities at Fraunhofer regarding the glass waveguide panel process. So we can manufacture glass waveguide panels on wafer scale, for instance 200 millimeter wafers. It means we have panels 140 by 140 square millimeters. We can also dice this wafer in a rectangle shape, so we have slightly different dimensions then. And we're using mostly shot D263T Eco so far. So we have a lot of multimode activities, and so state of the art is that we can manufacture glass waveguide panels in 305 by 228 square millimeters in the same class. And we have also shown a few years ago that you can have a dual layer waveguide integration. So then we use, for instance, 300 microns glass thickness, and because of the thermal diffusion behavior, and in case we have a mask opening of both sides, so we can integrate in the same process waveguides on both sides of the glass. And if the diffusion, or is the center of the waveguides located 25 microns below the glass surface, then we have a pitch of 250 in vertical and horizontal direction. So we also try to process and to handle much thinner classes, so that we have maybe much more optical layers into the PCB. And actually from the process it makes no difference, it's just only an handling issue. And so far we could show that we can manufacture panels. See, yield is quite low at the moment, but we got a few panels through having 145 micron thickness. And we, of course, we're looking to different classes. So we're always looking to what's new classes coming up on the market, because the glass companies, don't manufacture, or they don't have composition as special or made for this kind of application. So we have to use glasses from different applications, for instance, for the display application. And we really see strong potential for this kind of waveguide integration if we had a glass that's really optimized for our application. But this means the glass companies really have to see a huge market, that they really produce glasses in high volume. And for instance, we studied another class, it's this Corning Gorilla class, and it shows, for instance, that we can increase the propagation properties. So propagation loss was decreased in this kind of class. And we also looking on increasing the panel size. So at the moment we increase the whole process line to that we can process panels in the size of 570 by 400 20 square millimeters. Okay, and so I will hand over to my colleague, Bjorn, and he's presenting the second part, the PCB embedding technologies and photonics in PCBs. Yes. So they have always a great index profile, and actually, so we have, in case they have like the same effective index increase and the dimensions, you can compare it with the results that were presented in the presentation before. So we have very low dispersion loss and really low crossing losses.
All right, so good morning everybody. My name is Manessis. Also from my side, I would like to thank Dimitris, Nikos, and the whole team of Aristotelia here for the nice invitation and for the great organization of this workshop. You will allow me for 15 minutes to divert a little bit your attention, from classical and optical interconnections workshop, and I would like to add a new dimension in PCBs, where I will talk a little bit about embedded technologies for PCBs, embedding components in PCBs, and to alert a little bit your interest in this and in the direction. And then after 15 minutes, I will switch back in your very favorite subject. I'm coming from the embedded substrates and then the group of Fraunhofer AZM. Where, okay, pretty much, and then we develop a lot of, we developed the last 10 years and then embedding technologies for system and in packages. So if we have a little bit flashback and in PCBs. The word FR stands for flame and retardancy, and there were different kinds of PCBs. And back in 30 years ago, we have FR1. It was phenol resin with hardened paper with a brand name Bakelite or Pertinax. And as the flame retardancy percentage was increased, and more advanced FR materials were developed, so pretty much right now you will find the FR4, as all of you know. It is an epoxy resin with a glass and a fiber. And of course, if you want to increase the flame retardancy percentage, you can add also some fillers in the epoxy resin, alumina fillers, and you can go in a much higher glass transition and the temperature. Also, there are some niche materials for PCBs. There are PCBs based on Teflon, on polyimide, on a liquid crystalline and polymer, LCP, and the reinforcement there can be also ceramic or aramid. So here, this foil and it gives you and let's say an overview of a typical, let's say, FR4 manufacturing. So actually what you get is a very intertwined web of glass fibers coming in different diameters. So you can have the glass fibers in the weft and X direction in the warp, and then you feel you form this kind of very tight glass web, which is subsequently immersed in epoxy resins. And this and then a kind of very tight and then a web of glass fibers dipped in the epoxy resin then is semi-cured about 100 degrees Celsius in a B-stage format. This is very, very important in order to handle this kind of prepreg. Okay, we call it prepreg. And if you cure it, bring in a B-stage format, you can keep it refrigerated. You can use it within, let's say, the the allowed time for usage. It is absolutely stable at room temperature, and then you can do further your work making the FR4s. So typical, here just provides some maybe useful information for people who are not very familiar. I'm pretty sure that most of you know this kind of stuff. So the prepregs are coming in different types. A very quite thin prepreg is the 104. We usually use the 106, 50 microns, a very thin prepreg, 1080, about 63 micron, 2116, about 115, 120 microns, and 7628. Then what you do is you buy the resin. You have this very fine glass fiber mesh. You spend your nice euro. You buy copper foils that can come in many different thicknesses. So you can have copper foil in a thickness of 2 micron, 5 micron, 10 micron, 18 micron. Of course, you make sure that all the copper foils have the proper, let's say, processing in order to increase the roughness of the copper foil before it is laminated on the prepreg. So you laminate the copper foils with the prepregs, and then you form this buzz material, as we say, the substrate, the typical FR4 material. So this is a very basic foundation, for all the PCB in the house, or for all the laboratories that work, with PCBs. Now, I would like to introduce a little bit the idea of embedding, and pretty much all of you are aware, of assembly of components on PCBs. For those of you who have not recycled yet your old mobiles, if you break the mobile, or if you break any other no-value electronic device, you will see all the components on the PCB. This is very, very typical. And if you can recall also the nice foil from Bert yesterday, you could see that as we started assembling components on the PCB, they used thousands of wires to make the interconnections. So it still happens, but now the big tendency, or if you wish, the trend that we would like to bring the PCB is to put the components inside the PCB. So in this way, there are not any wires. There are very short interconnections, and you can make very flat packages. So this is what we call embedding. Please don't confuse it with embedded software or other terms on embedding, okay? So this foil shows a kind of evolutionary, let's say, road for packaging, for classical packaging, as we also look at, in our institute. So we can see, we call it first level chip interconnection inside the package. Traditionally, second level, I say that especially for the students, the second level is the assembly level in the packaging world. So the first level interconnection in the package, as you can see, you can have the component, this wire bonded, the interposer. You can use aluminum or copper wire bonds. Then a big step, radical step, I would say, in the middle of the 90s was, let's say, the invention, of the flip chip, or a package that has the same size as the chip. Then you could assemble the flip chip using, solder balls. And then we came with this idea of chip embedding, which is kind of the smallest, let's say, package in the 3D and the fashion. And here you can see representative pictures of chips heavily here bonded with aluminum wires. Here a flip chip, and here it is a device that I will show you later. So in this way, you can see really how we achieve to miniaturize, the packages, and what is the reason that you get, let's say, thinner and smaller mobiles and smartphones, okay? So we can see that, I would say in the 80s, beginning of 90s, we have this classical wire bonding of chip on a package and a substrate, and then we had encapsulation, and the packet size was quite larger than the chip size. Then it was quite a revolution at that time, let's say in the middle of the 90s, when, let's say, the packet size was about 1.2 times the chip size, but apparently the package was smaller. Then it was even a more radical, let's say, evolution, when we could really make the packets on a wafer level. So you can make, you can bump the wafer, you can make the device on the wafer, you can bump the wafer, you can singulate, and you can have a wafer level chip scale package, which actually the packet size is the same with the chip size. Then, as the ETRS had guessed, we have really the emergence, of the flip chip. That was really a revolution. If you compare that, the pitch here of the flip chip was quite smaller than the CSSP. Here the pitch of the bumps was about 200, 250. Here it was reduced significantly to 80, 120 microns. Very difficult, of course, to do bumping on such a small pitch. And after that, I would say in the last decade, about 2000, we started in Fraunhofer to introduce this idea of chip embedding, where actually the packet size looks like the size of CSP. It's about 1.2, 1.5 times. It really depends on the chip size inside the packets. But you can see that you have the interconnections completely with copper on top of the chip pads. So this is a more illustrative foil, how we do it. You can start with a very thin chip. Can be 20, can be 15 microns. Then you assemble this chip. You do die attach on a copper, on a substrate. So you attach your chip on the copper. Then you use this kind of epoxy resins or epoxy prepregs, what I showed you before. You laminate, pretty much you encapsulate the whole resin over the chip. Then you use a laser to open microvias on the chip contact pads. You do electroplating of the copper. You do structuring of the copper. We'll see more in detail in the next foils. So the features, of this, let's say, technology trend is that we can make very flat packages. Okay, we can make also very thin packages. We don't use any wires that have, of course, a bad effect on the electrical performance. We don't have any solder bumps. We have a direct copper contact to the chip. And also, as you will see later, this kind of technology is quite appropriate, for embedding also of power components. Advantages of this technology: reduce packet thickness. You can further stack these packets in a 3D fashion, improve electrical performance, low parasitics, low impedance, very good thermal performance, and this is very important because here, as I will show you later in another foil, if you use a thick copper and you have a powered chip, you can use also a heat conductive material to connect the chip on the thick copper, and you can make a very valid heat dissipation path for the chip. And of course, you have much better electromagnetic interference capability. Now, how does it work? Let me back up a little bit in order to give you the whole view, how we do the lamination. So this epoxy prepreg, as I said, is in a B-stage format. So we buy it in a B-stage format. You can refrigerate it. You take it out. When you start increasing the temperature, this starts melting, okay? So apparently the viscosity will increase a little bit, but about 80 to 100 degrees Celsius, the viscosity will start decreasing. And as you will see, it reaches always a point of minimum viscosity. This is the point that we'd like to avoid when we apply the pressure in the lamination press. And also, as you see, if you heat up with a different rate, you push the point of minimum viscosity at higher temperatures, and also the viscosity is the lowest. This should be avoided for apparent reasons that if you have a very low viscosity, you may squeeze out by lamination the whole resin and you may break all the components. So you don't want to work in a very high heating rate. You work about 3 degrees Celsius per minute, and keep that in mind when I will show you the lamination press profile. So what you do, this is a typical PCB lamination process. You apply, you heat up, okay, you apply temperature profile, and also you have to apply the pressure, okay? So heating profile is very common, you know, for the PCB. You heat up to 180 degrees Celsius, where the final curing takes place, and then the polymer is fully polymerized. So it is, let's say, C stage. And then you have a cooling profile. In the meantime, you apply very carefully a pressure of 5 bar in the beginning, and then only you have reached a temperature of about 80, 100 degrees, and the viscosity has stabilized. You increase the pressure from 5 bar to 20 bar. Okay, and you keep the pressure constant during the curing, you know, profile. Also, the whole process, and then, of course, needless to say, takes place, you know, into the vacuum. So you apply vacuum from the beginning. Okay. So this is, let's say, delineation of process. You can see you have a copper foil. The component, you know, is attached, and then they're using a dicing attached and a film. Then the epoxy prepreg is laminated, and also coming, you know, with a very thin copper foil. Alternatively, you have here 2 choices. Either you can buy a resin-coated copper foil, which comes already with a resin, or you apply the epoxy prepreg I showed you before and a separate copper foil. So you have this freedom. Then the next step, and then, that happened very, very fast. It was the opening of the micro vias on the chip and then the copper pads. You use a UV or a CO2 laser. Also here I have to bring to your attention that the UV is quite aggressive, so that's why you use a UV to open the copper and a CO2 laser to open, you know, the epoxy resin on top of the copper pad. Then you do copper metallization. Of course, by metallizing, you know, the whole structure, you deposit about 5 or 7 micron copper all over the surface, on the top and the bottom surface, and then you do typical lithography in process to structure, you know, the top and the bottom of the package. What I showed you before was the development of these embedding technologies for few components that they were thin. The reason was that this kind of resin-coated copper was very thin. It was about 80 microns. And as you understand, if you had 80 micron resin thickness, you go to work with components up to 50 or 70 microns. Now, a plausible question, or I would say a plausible interest would be, can we use this technology to embed thicker components, let's say components thicker than 50 microns? So the way you do it, alternatively, is if you have a thicker component, then you make cavities in your prepregs. So you set your prepregs and then with a cavity around, you know, the component, and then you use a cap prepreg to provide enough volume for the lamination. And again, you follow the same, let's say, process sequence. You use the UV laser to open the micro vias. You use a mechanical drilling to open the through vias here, and then you do electroplating. Another interesting feature I would like to mention is that you can open with a mechanical drilling even 50 micron hole, 50 micron hole with a mechanical driller. With a laser, the smallest via you can open is about 30 micron. Okay, so this foil shows you what we have in Berlin right now. I would say we are very, very lucky since November 2013, the new facility has been inaugurated. We're very lucky to get about 3 million euro from the government of Berlin and the federal government to renew the whole facility. So right now we have a facility about 1,200 square meters. Let's say a house for all these machines, and some of the machines Lars mentioned before. The whole new facility is about 2,000 square meters. 1,200 square meters is just a facility for the PCB. And as you can see, we're not really jealous of any other PCB house, so we're kind of prototype PCB house in the institute. We can process typical panels in a PCB industrial format, 18 by 24 inches in a panel. We have an LDI, laser direct imaging facility. We have machines for the development, the etching, the stripping of the resist. We can do, of course, automated electroplating, and this is a typical electroplating machine, our rad grabber machine, and this is a typical 24 by 18, so 18 by 24 inches panel. We have a laser driller, mechanical driller. We have facility to deposit, nickel gold or silver coating. Of course, we have 2-3 assembly machines, probe testers, and also some optical measurement machines to control the quality of our work. So, okay, just to give you an impression what can be, let's say, a PCB in a house adjusted, I would say, for embedding. Also, you have to realize that PCB houses were really very well equipped for multi-layer board and the manufacturing. They were not really adjusted for embedding. Embedding means assembly of the components. Before the idea of embedding was introduced, and then most of the PCB houses were subcontracting, the assembly. But right now, somehow, if they want to save money, they have to organize also assembly activities in-house. So this is a C-Place CA3 Siemens machine. With this machine, you can assemble all the passive components, even 01005, 0402, 0201 components, very fine components. Of course, you can flip also components. You do flip chip assembly. We have also a Datacon Evo machine where you can do very fine die attach, about 50 micron and thin chips. This is our Laufer press where we do the lamination of the epoxy prepregs on top of the substrates. This is also a Siemens microbeam, our laser, our UV laser. This is the mechanical drilling machine. This is our ramp grabber electroplating facility, fully automated. This is our Orbotech and laser direct imaging etching facility, and some spare also flying probe tester to test, the continuity of the electrical assemblies. Some typical examples, and then so you can see here. That was one of the first projects we have to do some basic, research. Here inside this package, we have a 50 micron thin chip. This is the chip. It is fully embedded, in the epoxy resin. Here you can see a typical via, 30 micron, and the anomalous shape of this via is really due to the fact that when you open with a UV laser the glass fiber in the epoxy resin, a lot of the glass fibers are sticking out, and then the electroplating is following, the shape of the fiber. Here is a typical X-ray, so you can imagine that it's an X-ray picture of this interconnects. You can see the microvia, and you can see down to the substrate where we have the, let's say, connection, the copper connection of the microvia on the copper line. So this worked very well. We did a lot of very extensive reliability testing. All these probes have passed MSL3, MSL1 levels of reliability, 85 relative humidity, 5 times reflows at lead-free temperatures, and no delamination was observed. Now, I would like to give you another dimension, and deliberately I brought this on a slide since the last, let's say, 5-6 years, even in the framework program 7, in the New Horizon 2020, they were talking so much about, a lot about the smart system integration. And when we talk about smart system integration, we try to promote in terms of packaging the system in package. So how you can put a lot of components in a small package, very miniaturized package, and which can be then handled very simply in assembly process. So in the framework program 7, not in this Horizon 2020, of course, which has started right now, I had a project for RF medical microsystem. You can see here that I have a very advanced system on chip. It entailed an RF on a transceiver. It entailed a digital signal on a processor, and very advanced features. And this SoC was assembled here on this substrate. The SoC was 2 by 2 millimeters, so very fine and about 350 micron thin. And then some other components also were assembled. You can see also the passives. But also for the first time, we attempted to embed MEMS, because MEMS are very sensitive in their packages. As you can see, we have intermediate frequencies, surface acoustic waves, RF SAV, bulk acoustic wave resonators here. And all these components now had different thickness. So it was a kind of bet for us if we can achieve to do the embedding without really destroying all the components. And as you realize here, the size is very small. So it was about 4 by 4 millimeters. So we're lucky, and I think we did well. Here you can see a typical cross-section, of the system in package. You can see the epoxy resin encapsulated on top of all the components. You can see the SoC. Of course, this cross-section doesn't show all the components. It shows only the system on chip and the filter. And you can see here this package. So this is a typical, panel. It has about 144 of these system in packages. These small packages are 4 by 4 by 717 micron thick. And if you singulate this panel, you can get many of these system in packages, which we call it a smart system in package. So you can imagine we don't have a real need to process this in 18 by 24 inches panel. This is what we call quarter format in Deutsch. So it's a quarter of the large format. So it's 9 by 12 inches panel. Okay. So we have full capability to produce in a much larger panel. So you can. So I forgot to say also that in this package, all these are about 20 components in this package. So there are components inside. Now another perspective I would like to add in my presentation is how we can use this embedding technology for power applications. And the reason that we moved in this direction is that there is a very big initiative from the German ministry, a program of about 2 billion euros up to 2020, for green energy, renewable energy, and also electrical cars. They do have a very ambitious goal there to have about 1 million electrical cars by 2020. I think they should be happy with 500,000. And over there, we have to step up and also to offer, let's say, embedded power for the electric car. We work very intensively with Continental, Daimler. All of you know Daimler. Continental, for those of you who are not very familiar, doesn't only make tires, but also make parts for the automobile and industry, so airbags, brakes, and gearboxes, just for your information. So, but now it was very interesting concept we developed here. So we had a lot of IGBTs that can handle a lot of voltages. These IGBTs and then come with a silver interface at the bottom and also with aluminum. And the concept we developed here was very interesting. We started using very thick copper because in the power application you really need to dissipate heat very effectively. And you assemble these IGBTs and using a kind of silver sintering adhesive, which has about 150 watt meter Kelvin. So in this way, you promote the heat dissipation, you know, also in the Z direction from here. We call this power PCB. Then the power PCB is further assembled with a thermal grease or with a soldering on a kind of cooled heat sink, and then you have an effective cool down, you know, of the system. On top, you have the freedom to assemble your capacitors, your reductors, or you can have also the control unit, the controller unit, you know, for the motor. So this kind of power modules is used for a motor control unit, 10,000 watt and switching power. We have also another project right now with 50,000 watts, so 50 kV. So very interesting for us to further, let's say, diversify the utilization, you know, for embedding technologies. And here it's the last slide, concentrated on medical applications. That was also a main focus of our group the last 5-6 years, where we can see a module, again, a system in package for a medical implant. We call it power system in package. It was, I think it was consisted of 9 embedded MOSFETs. Okay, here you can see another medical and then a module for electroshock used, you know, from an American company, where you can see 3 embedded chips. Here is the resin, of course, sorry, there's not any contrast between the resin and the chip, but believe me, here is resin. So we have, let's say, a stack, you know, of 3 chips, and of course the whole package is coming, you know, with solder pulse. Also here it is a cardiac pacemaker module. You can see an embedded microprocessor. Has been flip-chipped and then assembled before we do the lamination of the epoxy resin, and here are the surface mount components on top of the embedded packets. And here you can see another power application with 4 thyristors handling 400 watt and 45 ampere. Here you can see a cross-section of one of these 4 thyristors. So right now we're working very intensively, I would say, in power applications, since I mentioned we have this very strong industrial, I would say, incentive. The last slide gives you, let's say, the status right now of embedding technologies in Europe and internationally. Of course, there was some embedding concept from 1968, the first patent. Then our group was the first group in Europe to initiate, you know, the idea of embedding and to do some basic research and development through the Hiding Dice EU project, where we learned how to make microvias. We acquired our first machines. We make, you know, the first embedded components, and we stacked also different embedding packages. Then we came up and we got funded with a very large IP project in 2005 with the name Hermes, where we actually teamed up with PCB industry, and we taught a little bit PCB industry how to do embedding. In this way, we mobilized also AT&S in Leoben in Austria, and right now AT&S is integrating, you know, embedding technologies in their manufacturing, you know, floor. Of course, they are not really very favorite in doing heterogeneous integration of many components, because it is very difficult to assemble all these components, but they do the manufacture embedded products with 2 components, let's say DC-DC converters, and for the industry. And you can see here that the production